So welcome, everybody. By the way, my name is Bob Birgeneau. I'm professor of physics and therefore fellow faculty member with George and also chancellor of UC Berkeley and also a staff scientist at Lawrence Berkeley National Lab. And obviously today's a wonderful day both for UC Berkeley and for the Lawrence Berkeley National Lab. And we're, of course, greatly honored to be celebrating a Nobel Prize for George Smoot, professor of physics at Berkeley and an LBNL scientist. And, of course, there are few more exciting moments than this in the life of a university. And our campus is enormously proud of George's achievement. Actually, we and the lab were proud of his achievement before the Nobel Prize Committee recognized what he had done, and we're even prouder now. We're also proud for the committee that they recognized this great scientific achievement.
Does this mean I'll get a raise?
George, I have to talk to your department head about that. I was going to come to it. Actually, George could get a raise just for his teaching, not even counting his research. I think all of you know that the experiments for which the Nobel Prize is being awarded represents a technical tour de force which successfully probes the most fundamental aspects of the universe. This work is at the heart of understanding the origin and evolution of the universe, moving cosmology from the realm of theory to experimentation and giving us the data to test these theories. And as an aside, one of my personal friends is responsible for the theory that George's experiments test. And I remember having a discussion with him around the time that he invented the theory, and we agreed it would never be tested experimentally because it was too hard. And here we are, extraordinary. I want to say this work of George's also demonstrates the great power that emerges from the synergism between our campus and Lawrence Berkeley National Lab, and you will see many more examples of that in the future. This research was led by George Smoot, together with John Mather of the NASA Goddard Space Flight Center in Greenbelt, Maryland, who, as you may already have noted, received his PhD from UC Berkeley in 1974. And he was a student of Paul Richards. I don't know if Paul is here. Anyway, okay. George is, of course, as all of you, not only a brilliant experimentalist, but as I indicated already, one of our very best undergraduate teachers in the physics department. He not only teaches undergraduate physics, 7B, I think it is. George?
We were talking, you know,
Monday, Wednesday, and Friday at 11. Is that right? Exactly right. Right. So it's Tuesday, so it's okay. And he has 4 undergraduates who work in his lab in our undergraduate research apprentice program. And so he's a paradigm of a teacher and a researcher, and what we believe we stand for at UC Berkeley. Today's Nobel Prize is the 20th for UC Berkeley and the 8th Nobel Prize in physics since E.O. Lawrence won the first Nobel Prize for us in 1939 for his work that created the prototype of the cyclotron. And today, with the award to George Smoot, we have 7 current Nobel Prize winners, and I want you to know, George, Steve, that that your parking spot is being labeled right now.
Actually, I have bad news, George. It's just going to say NL. This is really a happy day for all of us here at LBNL and also UC Berkeley. it's even happier, I would say, for us at LBNL for the following reason. George came in as a postdoc to the Lawrence Berkeley Lab in the famous Group A, the Alvarez group. And this group has spawned many great physicists where they started their career in this group and really went on. And then eventually UC Berkeley gets wise, but but anyway, but seriously, actually, before I go on and make my own personal remarks, I have a little crib sheet that's actually I want to read some comments from the Secretary of Energy, Samuel Bodmin, and the Undersecretary of the Office of Science, Undersecretary of Science, Ray Orbach. So Sam Bodmin says, I offer my congratulations to George Smoot and John Mather for their outstanding contributions to science, which is being recognized with the 2006 Nobel Prize in Physics. The groundbreaking work of these two American scientists showed us how to look back in time to the very infancy of our universe so we might better understand how it came to be and where it is going. They began a scientific journey that we are still on today, one I am sure will lead to more amazing discoveries in the future. And from Ray Orbach, the DOE Office of Science supported George Smoot's research during the period in which he worked on the COBE experiment, and we continue to support him today. In addition, one of the principal instruments for the NASA COBE experiment used to make the discoveries was built at the Berkeley Lab facilities maintained by the Office of Science. This is an example of the scientific excellence the DOE supports. Another quote, which wasn't sent today, but this was from Stephen Hawking at the time of the discovery, and what he said was the evidence for primal lumping that seeded the structure, the stars, the galaxies, the clusters, was the greatest discovery of all time. Well, it's certainly one of the greatest discoveries of all time. Let me try to explain what it was all about. And actually, so the rest is going to be ad-libbing. In 1900, Planck tried to describe mathematically a type of radiation where this is if you take a cavity in a little hole, and what type of radiation, a metal cavity, what type of radiation comes out of this little hole? Very simple problem. And using electricity and magnetism. And he found that in order to describe experimentally the radiation, he had to assume that the radiation had to come in discrete lumps. The frequency of the radiation times some universal constant that happened to be called later on Planck's constant. In this description of the radiation, which was one of the real foundations of all of quantum physics, was implicitly that the radiation could not go lower than a certain minimum energy. Okay? And this then was transformed later to say any particle that's localized somewhere had to have some minimum energy. It could not be cooled to zero energy. It had to have some inherent, what we call now quantum fluctuations, little jiggling. Then in 1964, okay, then time passes. In the 30s and 40s, scientists Herman, Gamma, Beta, I guess were there any others? Alpha. In fact, Beta was thrown in so there would have to be Alpha, Beta, Gamma. Gamma. Said that maybe if the universe started as a Big Bang explosion, there should be some remnant of this. In 1964, it was discovered accidentally by two scientists at Bell Laboratories, and said there's some radio hits out there, and it seems to be cosmic. It's not associated with the galaxy, it's not associated with the solar system, not associated with anything except the whole universe. And in order to see whether this is something that the initial proponents of the Big Bang had to do, there was then a concerted search to say, this was one particular measurement at a particular frequency that said there's this radio hiss coming out there, but is the spectrum what Gamow et al. Predicted? And the spectrum would be that of Planck's so-called black body radiation of 1900. And so what this experiment did, there were two parts of it that were cited in the Nobel Prize. The first part, that was led by John Mathard, said that yes, indeed, it's black body radiation. Not only that, it was the most perfect form of black body radiation ever discovered. You couldn't make as good a source in the laboratory as what they found in space. The second thing, which was even more startling, was that it was not only a measurement that, yes, indeed, it fit the black body structure exactly, but then as you went finer and finer and finer, not a 10% measurement, not a 1% measurement, going down to a part in, really a part in a million, but a part in 100,000, they made a measurement that said, no, there's some little ripples below that, a part at 100,000. This was the more exciting discovery in my mind, and that was led by George. The discovery was that there were these little ripples. These were ripples that invariably led to the seeding of the galaxy, but there's something even deeper than that. It's still speculation in part, but there's a lot of weight, and that is, let's go back to quantum mechanics and these little fluctuations in quantum mechanics that would never go away. That's an inherent part of the entire theory. That quantum mechanical fluctuation, is it so far okay? Is the audience following this? All of those who say yes will get a raise. They're following it. Anyway, so these quantum fluctuations then expanded in an inflationary universe, and that was the reference that Bob Birgeneau was talking about, that the universe went through a very rapid expansion. And the ripples that George and his colleagues saw were a remnant of these, we believe, of these quantum fluctuations. While he was doing the measurements, it was a very exciting time. One of the other co-founders, along with Alan Guth, of the inflation scenario was Andre Linde, who was at Stanford at the time. And as the results began to unfold, they saw just plain beautiful black body, another factor 10, beautiful black body, another factor 10, beautiful black body. Kept on going lower and lower. And Andre, and this is the test of a really great experiment, a theorist was willing to concede that he might have been wrong. And it was only in that last factor of 10 that began to see those ripples, or last factor 3. And it was at such a low level that there was a feeling that that was the quantum fluctuations, the minimalist fluctuations. Now, George was misquoted soon thereafter. And so I'll here go on record. I just found out this morning that it was a misquote. It made a big splash then, a huge splash. And George was misquoted as saying, you know, of this discovery, I've seen the face of God. He'll tell you the right quote. And he didn't say exactly that, but then in putting in context of what Stephen Hawking said, this is how important this discovery is. That is truly of fundamental importance. It truly tells us something remarkable about our universe, that it links the quantum physics we know with the cosmology that has now become a precision scientific set of measurements, from philosophy to precise physics. So it's a great day for Berkeley Lab. It's a great day mostly for science, and of course it's a great day for George. So George, the show is all yours. Enjoy the moment. Your life will have changed forever.
I guess you're wondering why I called you here. Actually, it reminds me of a time almost 15 years ago when I came back from the APS meeting announcing the first discovery from the first year of COBE data. and this auditorium was full, not so much press, mostly scientists wanting to hear about what's going on. And so I don't want to spend so much time talking about the science. I want to actually say first a lot of thank yous, because I had a lot of colleagues. I led the team, just like John led the team. So we had a whole group of people that were involved with us. And it was not only just scientists, but there were a lot of engineers and technicians and other people who did a tremendous amount. And when I wrote my book, in the back of it, there's several pages that list over 1,000 people that contributed to the satellite. But it wasn't just that. And for me, it's been special being at Berkeley, and it's been particularly special being at the Lawrence Berkeley Lab, because it was a place where I was not only given the freedom and the resources to do the research, but shown a style of how to do research that was a style that was very different. I came here from MIT, and we had a way of doing things at MIT, which was quite impressive and quite good in its own. And I came here, and it was a very different style that came from our founder, from Lawrence and Oppenheimer. And it was, pick out the best science you can do and do it, and don't worry about it, just go ahead and do it. And that was so liberating. And while at MIT, we were sort of taught to do those kinds of things. At Berkeley, it was, it's no wonder the free speech movement started here. It's the free science movement. Do the best science you can. That was the thing that really made it so that I could think about doing science that was out of the ordinary and into a new field. And I want to thank the Department of Energy for maintaining these labs, and particularly the Lawrence Berkeley Lab and its environment, and the university because of the great resources, the intellectual resources that were brought here, and of course NASA and all the taxpayers. They would, you guys paid for this, and I figured it out once. It was like $3 for every person in the country. so thanks. And I say that collaboration between NASA and DOE was an extremely fruitful one. The NASA really knew how to run space missions, and the DOE, especially the Lawrence Berkeley Lab, knew how to invent new instruments and think about new science to do. And the combination of those two worked extraordinarily well. And we're hoping that that kind of partnership will go on in the future. And so there's a whole lot of other people that I could thank and I would like to thank, but I don't know how long you want this conference to go on. And it makes me feel like it's the Academy Awards. It's more fun, if you guys can, give me an Oscar or something. But I'll settle for the Nobel Prize. All right, so I think unless you guys want to hear some more, I can take some questions. Hi, Key. Good to see you again. Thank you.
I want to ask you a question about follow-up research. The WMAP results got a lot of attention a couple of years ago. But I'd like to know, how do you see the historical continuity between COBE and WMAP and whatever's coming next?
Yeah. Well, the next thing, that is one of the things that I'm working on, is the MaxPlanck Surveyor. You heard from Director Chu that Max Planck is the one who started the quantum age. So our next satellite, which we think is going to be able to do quantum stuff, is the MaxPlanck Surveyor, which is mostly a European Space Agency with some NASA component and some DOE component in it that is going to be our next launch. And when I set up my teaching schedule, I thought we would be launching this spring. That's why I'm teaching lower division class this semester instead of next semester. But unfortunately, it's been delayed for about a year. But WMAP continues to take data. And we have a nice little movie that shows the COBE map, and then it transitions to the WMAP results, and you can see how tightly they compare, how much reproducible that was. And the thing that both Birgeneau and Chu talked about, which was these are the fluctuations that grows in galaxies, that's part of the story. The other part of the story is that you can actually learn about the composition of the universe. You can learn about what happens in the early universe. And so the analogy that I like to give to that is that if you hear the Campanile bell, so if we were down on campus, right, and sometimes during the prelim exams, when the Campanile bell rings, I ask them to estimate the Q of the bell. That is how long it takes to damp out and what the frequency is and so forth. That's that's a physics in joke. But if you got to be able to answer that question to get on to grad school. But if you listen to a bell, and you listen to them enough, you'll be able to tell whether it's a brass bell or a steel bell or a cold iron bell or something like that. And what we're looking at with these fluctuations are the ringing of the early universe. It's this situation where there were quantum fluctuations put in the very early phase, probably inflation. It caused this, it's like hitting the podium with a hammer. You can tell when I hit it's all the frequencies and they get spread all out and get damped out. You hit a bell, you also excite all the frequencies, but the bell selects out frequencies, right? The bell selects out its characteristic frequencies that match the shape of the bell and the material of the bell. And the same thing is true for the universe. The universe was bammed at the beginning by God or whoever, right? Depends whose face you see. And there's this big shock to the whole universe, all frequencies are excited, and the universe, because of its constituents and its geometry, picks out certain frequencies, and by looking for those you can see. And that was the thing that makes it why, once Kobe made the discoveries, we now know we have this new tool that we can study the universe and follow up on it. That's why WMAP was done, trying to measure why we did the balloon experiments to try and measure the geometry of space-time, why we did why WMAP was done, why we're doing Planck. The more carefully we measure these variations across the sky and look for the frequencies being picked out, right? We don't have it should be on the blackboard here. It's hidden there. but because I'm sure I explained it to my students many times, you can, by looking at those, find the constituents of the universe, that is, what the universe is made out of and how it's developed over time. And so it's not that you just are seeing that galaxies form from these fluctuations. These fluctuations and how the universe is made up tells us how the universe rings and tells us how to make a model of the universe. And the thing that was surprising that Birgeneau and Chu refined to, people were very worried because as we got down lower and lower limits on the fluctuations, it got to be hard for gravity to make it. And then we had to resort to having dark matter. And then it turns out the fluctuations we saw were just a factor of 2 bigger than they absolutely had to be in order to make things work. And so had I been really smart, I would have said, wait a minute, I really believe that factor 2. There's something else in the universe. Well, it took a while, and Saul Perlmutter and colleagues had to come along and show that there was this dark energy, and that's why the universe is accelerating. So Saul will be up on this podium some days later, right? Some years later. But the seeds and stuff are all there. We can't do everything from the cosmic microwave background, but we can do a lot. And we're really in a different regime where we're not only understanding what the universe looked like when it was an embryo, but we're actually trying to see what the genes, what the genetic makeup of the universe is and what the constituents of the universe are, so that we can predict its whole development and understand it. And that's, to me, that's the really exciting part. So today is a great thrill. It's not quite the same thrill as making the discovery and having to keep it secret for months before we made the announcement.
So. For the general non-scientific community,
yes.
I could ask you just about the emotions of the day and getting that phone call.
This is really surprising because usually you hear rumors and so forth. I was absolutely convinced, and so if you look, we've been revamping our group website, and it's only half redone. So there's some direct evidence that I didn't expect to get the prize this year. It was not anticipated, and I was particularly surprised because my number is unlisted. I don't have a phone. I have a cell phone. My number is unlisted. And the phone rang in the middle of the night, and usually I can't hear it, but I heard it. And I got up, and it was this, these guys from the Swedish Academy. And I'm going, how did you get my phone number? And it turns out they called around, right? And pretty soon my neighbor's over knocking on my door saying, hey, we got a call. So we gave him your number. And it turns out that Jeannie Miller also gave him the number and so forth. And so they called, and at first I thought, well, I better be careful. This could be a hoax or something like that. But the guy sounded really serious, and the next guy sounded really, and he had a Swedish accent. And so, I thinking, well, I better take him seriously. And so finally, somebody I knew got on the phone, and I thought, oh, this is either a really elaborate hoax or it's this is the real thing. And I was kind of believing it, but I thought I better get on the web and check, right? So, I went to my computer, you know, and I pulled up the page, and there's nothing there. It's not announced. Right, and I thought, oh, well, maybe not, you know. But wait a minute, you know. I looked at the time, and my watch wasn't on, so I had to look on the computer, and it was time. It was already time for them, and so I waited a minute, and I got another call in the meantime, and I thought, this is strange, you know, people calling in the middle of the night, and then, you know, I clicked, the web page comes up, and it announced that John Mather and I have been awarded the prize for leading the teams that made these discoveries and these measurements, and. You know, and then the phone hasn't stopped ringing since. I mean, it's been sort of continuous. And so, how is it? Well, it's kind of exhilarating. You realize that I'm still a little hyper from 3 a.m., right? You know, and and so forth. It's very different from the thrill of knowing you've learned something about the universe that nobody else knows yet. You know, I can remember walking down the hill, you know, and you know, really late at night. Because finally my grad student had redone the calculations I had done, and it was confirmed in a different way. And I thought, okay, now I can start believing this. We really have discovered that there are fluctuations in the early universe. We really do know something about the universe from the first tiny fraction of a second. And it's like 1 a.m. or 2 a.m. in the morning. The traffic light, I don't know, you can probably tell because the traffic lights were blinking, whatever that means. So I'm walking down the hill to go home, and it's like I'm floating. Right? And it sort of felt that way. And then I had this huge amount of work to do, right? But it's sort of, it was this sort of glide feeling you have, you know, for something. Now this is just like pretty amazing. The auditorium isn't quite as full, but that's because there's nobody sitting in these rows. But, you know, so it was a really big deal in 1992 when we made the announcement, and then when the succeeding years followed up, and then when WMAP came along and found the same thing and extended it, and likewise for our balloon experiments and so forth. And so it's a really great feeling to make the discovery. It's a great feeling to be honored, but in fact, the honor should go to the whole team and to the funding agencies and the taxpayers and everyone else. I mean, you know, they didn't get to have the fun of, you know, staying up late at night doing calculations. But, you know. No more questions? Oh, this was easy. Well, I could talk more, but I think I should take questions.
George, I could ask a follow-up question.
Sure, Key.
I mean, typically people talk about these things as the seas without which we wouldn't be here. There'd be no galaxies, no stars, no planets.
Right.
Talk a little bit about that.
Right. To me, it's absolutely fascinating, and that's why I like the idea of inflation, why, you know, Andre Linde and Paul Steinhardt, these people who worked on inflation. At the beginning, I thought, well, that's an interesting idea, but, you know, but then as we started seeing the fluctuations and seeing that they extended on scales that were way beyond where light could have traveled in a reasonable time, I started taking inflation more seriously and saw what a beautiful idea it is. The idea that tiny quantum fluctuations can be blown up by inflation, you know how prices rise, but by inflation, by this exponential growth of the universe to where it's of sizes that our own galaxy was once a cosmic fluctuation, is extremely beautiful idea. This is sort of in literature the equivalent of a haiku, right? That 17 syllables make this, you know, this beautiful statement. You're saying some tiny quantum fluctuation through a simple mechanism of inflation and then the coasting afterwards grew to be our galaxy. But not only that, the ones that happened a little earlier, they're a cluster of galaxies. So you can look at the Coma cluster of galaxies, the Virgo cluster. Some clusters have hundreds of galaxies, some have thousands of galaxies. You know, the fact that galaxies were once tiny, such tiny things that quantum mechanics was dominating is really a beautiful idea, and so forth. But then when you start putting all the pieces together and start thinking about dark energy and about this, the fact that you can put in, say, 14 or 15 ingredients, some laws of physics, and turn the crank, and you get the universe, that's pretty impressive. You know, whoever designed this did a really great job. You know, it's it's like, you know, I couldn't have made a model that straightforward and that simple. And it's like, why did it need the dark energy? Well, I don't know, but we're going to find out. You know, and how precisely do we need to measure all these parameters like the expansion rate of the universe, and what fraction is ordinary matter and neutrinos, and what fraction is dark matter, and what fraction is dark energy? You know, we're going to measure all those things very precisely, and somehow we're going to understand how the universe fits together in a really, you know, a really smooth and clear way.
You're mentioning into this category, but can you set straight the story of the face of God quote?
Gee, I would think somebody know that. There was an issue when I was explaining, we found the largest structures ever seen, and we've seen the seeds for what is eventually going to turn into galaxies and clusters of galaxies and break apart and to become stars and so forth like that. Then people were saying, well, what does it mean? What does it really mean? What's this really like? And so I gave some examples, and I tried to explain this and so forth. And out of the 4 or 5 examples that was there, one of them I said, they were saying, well, yes, but how important is this? And there's all this excitement, but how important is it? And so one of the examples that I gave was, if you're religious, this is like seeing God, right? And that very quickly became, scientist sees the face of God. And, and I actually have saved some National Enquirers and a couple of magazines like that, which have the Derby picture, the third instrument, which unfortunately didn't get mentioned, headed by Mike Hauser. The third instrument was the one that measured diffuse infrared background glow, the glow from the first generation of stars and so forth. That experiment also made a very beautiful picture of our own galaxy, showing that it's a beautiful disk galaxy with a bulge in the center. And in my copy of the National Enquirer of the World Press, there is that picture with this Greek column building of monstrous size, with an arrow pointing to it saying, look, the abode of God, as seen by Kobe, right? And so, there is an interesting thing, but to me, the issue here is that this is kicking off a phase where we are actually starting to have a scientific explanation of how the universe was being created and developed, which replaced the myths that every tribe and every country has, to a sort of a global story about how the universe came into being and what is our place in the universe. And this is sort of a unifying thing for all of humanity, and in terms of it. And that's why you see this is something that science is something that spreads across all the cultures more than any other thing. And why we are continuing to push forward in these cosmology experiments, both to really measure these parameters of the universe and see its development and cross-check it, and to try and find out what is this mysterious dark energy and this dark matter. There's many experiments going on to try and do that. There's a lot of unsolved mysteries yet, and we still have a lot of work to do. That's the fun part, right? We can just hope there'll be one more discovery. I personally have 2 students working on trying to search for cosmic strings, which are, relic from an early universe. When you go through a symmetry breaking, where you have a rotational symmetry that gets broken, and some things get left behind, like wiggly worms in the early universe. And I hope to find that, because that would just give us a window into the tiny fraction of a second in the early universe, or it might even be an example of a superstring, made manifest in part of the universe, if brain inflation or something like that. So now we have multiple models of inflation, multiple things, and we're trying to distinguish between them. So the mystery of the universe is not completely solved yet, but we're getting in the outline of what the later universe looks like, and we're pushing the frontiers out. And so we have this analogy, right? This is what we know, and the boundary is our ignorance. And our ignorance has never been greater, because what we know has never been greater, right? And the probes that we're pushing out are letting us do that stuff. So that's the fun part, right? That's why science is a great career, right? So young people, become scientists. Boy, this is a quiet group.
Happy to ask a third.
Okay, go ahead.
I'm going to ask you this question, George, because so many people have asked you the question, and I hope that you can grapple with it as best you can. You have, of course, attracted many people, as Darwin did, who have religious concerns and who correctly or incorrectly misinterpret what you've done in their own agendas. And I just wondered if you could address that a little bit, if your own personal views on this might be of value to you.
Well, this was actually quite interesting, because shortly after the announcement, I came back here and gave an hour and a half, 2-hour talk here in this auditorium. And then I was scheduled to teach at a school in Amsterdam, but I was stopping by Oxford and Cambridge just before that. And so Stephen Hawking invited me to a dinner and to give a lecture there and so forth. And the interesting thing, so I got a day in London on my way to Amsterdam, and an interesting thing going on was there was a conference of Anglican bishops and church going on at the same time. And so the press coverage in England turned out to be extremely extremely greater in England than in the United States, even though it was very impressive here in the United States. And the reason was it was bouncing between the front page, the science page, and the religious page, because the Anglican bishops all took this as an example of the creation and, you know, how we're understanding what's going on. And so what I have found in general is that I was careful in what I tried to say, and most people did not find this an attack on religion or anything else. I think the climate is a little different now, that, you know, between 15 years ago and now, that there are more people who object to the idea of the Big Bang and so forth in churches than before. But at the time, there was quite a lot. But in England, the press coverage continued for 2 weeks solid in the front page and everything like that. And there would be radio programs, and I was called, you know, over in Holland, I was called to be on radio programs, and there would be a scientist and me, presumably a scientist too, to make the odds better, and one or two people from the church, and we would have a roundtable discussion on the phone. And it didn't seem to be a problem, but you understand that people in England are a little more reasoned in their discourse than in the United States, perhaps at the present time. But I did not have a problem, and I have relatives that live in Texas, and I got invited to go to their church with them, and so I guess I wasn't a complete pariah in the situation. I actually have found that it hasn't been so much of an issue, and that is probably something that Lemaitre found, you know, back when he was formulating the Big Bang theory. He could be, you know, an abbé, or basically a priest, and still work on cosmology. And as some of you might know, the Vatican actually runs a cosmology school, and you know, because they got to keep up on this, they don't want to get caught by surprise like Galileo, you know. They learned, you know. And so it's you know, it goes to show you that some people can adapt and so forth. And in Germany, it was a lot more complicated. You know, the Germans have a much different opinion about this, and they thought it was good, and they thought it was, you know, pretty interesting and so forth. But they really got excited when Tipler came up with the idea of resurrection. You know, that there's an omega point at the end of the universe, and you have now enough free energy and everything. You can reconstruct the entire universe, including the souls. And so, you know, that just sparked a whole revolution in theology in Germany. And so, you know, it just depends, right? Sometimes science is an input into religion. Sometimes religion is an input into science and causes people to look at things. And so it's just to see. I haven't seen there being a really significant conflict between the church and science up to this point. And so I hope it stays that way.
Can you describe in the simplest of terms precisely what you've won the prize for? How long it took?
Actually, believe it or not, I haven't had time to read the citation. It somehow, you know, the phone kept ringing, and then I had to come in, and they were showing me around, and I was trying to get pointers from Director Chu on like how to handle the chaos, because I still have to give a class and an exam tomorrow, you know. And so I haven't read it, but what I believe the citation was for the 2 parts of the Cosmic Background Explorer satellite, COBE for short, which measured the properties. Oh, thank you. Yeah.
There it is.
All right. All right. So the experiment for which John Mather was the PI, and I was a co-experimenter, and he was a co-experimenter on mine, there were originally 6 senior members of the science team, and then 19 official members, and then there was another 20 or 30 people who were hired too late to get the NASA seal of approval, but I still consider part of the science team. And there were a huge number of engineers and scientists. The citation was for the instrument team, or the observation team headed by John Mather, was for measuring the spectrum of the relic radiation from the Big Bang and showing that it was nearly an ideal black body. That is, it's characterized by a simple number, a simple temperature. And it is, for those of you that like physics, it's the thing that has the most entropy, that is the most chaos in it, that is the most scattering. That what happens when you have radiation, you throw it in a box and you scatter it as much as possible and let it come to equilibrium, it will form what is called a black body curve. And that's what's happened in the early universe, that all the energy that was in the early universe got scattered around sufficiently that it became the black body radiation, this radiation that Planck was able to first describe successfully. And so the FIRS instrument measured that with extreme, that's the instrument that John Mather was the head of the team, measured that with extremely high precision And we had to go to a lot of trouble to cool the entire apparatus down to about the 2.7 Kelvin, 2.7 above absolute zero, which is like minus 450 Fahrenheit, for those of you that have trouble. It's really cold. There's not much, wiggling going on for the, heat is the atoms wiggling around. There's not much wiggling going on. And it's just the quantum fluctuations that are dominating at the temperature. We had to cool it to that and had to build a very special kind of absorber that was folded on itself many times so that light couldn't get out without scattering at least 7 times in order to get something that looked good enough as a black body that we could compare it to the sky. And so that was also a very precise measurement. And what it did was establish the fact that the radiation had come into extremely good thermal equilibrium in the early universe, and it's very difficult to do that without having a hot, dense universe at the beginning. What my experiment did was to make a map of that radiation, and very much the same way a TV picture does it. We scanned across in lines. Well, these were oval lines, but never mind. We scanned across in lines, and we summed all the lines together and displayed that as a map. And of course, we had to scan millions of times because we were looking at a signal which is very low signal. And so the noise of the receiver and the noise of the residual galaxy and so forth were things that we had to average over and make sure we got rid of it. And so we're talking about a very low signal level. The sun is 6,000 degrees, the Earth is 300 degrees. This is below 3 degrees. So we're looking at a signal that's very, very low. We had to look at this, and we had to map it very carefully. And so it was a low signal to start with, and we had to map it to about a part in 100,000. In fact, eventually we got to nearly a part in a million. And when we did that, we saw there were variations across the sky, and these variations seemed to be independent of scale. That is, the variations that were very large across the sky had an average fluctuation. We call it root mean square, but the average fluctuation away from the mean was roughly a part in 100,000. And when you went on to each smaller scale, you saw roughly the same fluctuation. That is, something put in the universe fluctuations roughly equal amplitude, average amplitude, randomly, stochastically, but average equal amplitude, all the way from the smallest scales to the largest scales that we could measure. And this was a difficult thing to do because just any mistake you make is going to look like random variations, right? And so the whole trick was to do it really carefully and show that you were seeing something from the universe rather than from your equipment or from the galaxy or for something else. And so the team deserves a tremendous amount of credit for really being careful, right? That's what it came down to. And so once you see that, you realize, if I just extend this on out, I can easily make the galaxies, I can easily make the clusters of galaxies, and I can predict there should be even larger scale structure than that. Now we know the dark energy keeps things from being much bigger than a big cluster of galaxies from forming because it makes the universe move apart faster than the gravity's clumping it. And so there's a natural cutoff. But how can you make something across the sky that goes from here to there, right, when you've only had this much working space, right, in order to do it? So you needed a mechanism. That's the reason inflation is, his name gets invoked. And there are alternative versions of inflation now that are like, we happen to live in, 3 spatial dimensions and 1 time dimension as far as we're concerned, but there are other dimensions out there. And you can imagine here's a world that's 3 dimensions plus time, and here's another world, and it's an anti-world, and these would be attracted to each other, and they would collide, and when they collide and annihilate, they produce a lot of energy, and if this is, like the elephant birthing, another elephant's baby, this guy gets to, the brain next to it, the 3 plus 1, it could produce it can be the universe, and it's all got all this free energy and so forth. So there are various ways you could make the universe, and we're trying to study and understand. That's why I have students working on trying to find cosmic string. That would be one of the signs of this breaking. But also, we know the forces are unified, and when the forces deunify, it's possible that there are ways that way. So there are still relics that you can look for in the universe that you could hope to find that'll tell you about what was it that allowed these fluctuations, these quantum mechanical fluctuations, to grow on such large scales. And so, there's still work to be done, guys. More questions?
Okay, I actually have one more question. Now that you've been in Stockholm, you're going to be a principal spokesperson for science. And could you comment on what you think would be best for the world, but the United States, Berkeley Lab, in terms of laying the seeds for the next generation of great discoveries?
All right, well, here's my chance to thank the lab again, because it really was, I thought, a real thrill for me and a real opportunity for me as an undergraduate graduate student to go to MIT and get to work with the great people and see those great things going on. But when I came to Berkeley, I was introduced to a new scale of physics, and it was particularly the people at Lawrence Berkeley Lab, where people said, think and dream of big projects, think and dream of new ways of doing stuff. Don't just think of how to improve the experiment you're doing, or think of staying in the established field. Think about branching out and making a new field. And I think that that is a tremendous heritage that Berkeley brings. You know, it's not only do we have free speech, but we have freedom of research. That's a real freedom of research in the sense of what's going on. I would think that, and one of the things that I did see is when I get money from the NSF or from NASA, it's for a particular project or a particular research effort, whereas in the Department of Energy, there was a block grant that said, okay, the people here, you guys decide what is the best way to spend that money and go after that. And the directors of the physics division said, okay, if you guys have an interesting project, come to us and we'll give you some seed money if you want to. And that's how I got started in the cosmic microwave background. It was Louis Alvarez saying, don't just do the same experiment you were doing, think about what next. So I thought about him, and so did my colleagues. And we came up with a number of different ones, and we did some different experiments. But I was able to go to the division head and say, I'd like some seed money to start this project up. And they said, fine, go ahead. And I said, well, yeah, I'm just a young punk kid, you know, what kind of controls are you going to have on me? He says, here, take the money, do great, or get out, right? You know? I mean, and that was just you know, given that opportunity was really special. So I think the thing that there are a couple things that I could think of that would be great. One is for the DOE, which was always the stable funder, and you know the federal agency that was sort of a steward of science, and everything, that they would make it a policy for their national labs, or at least for this great national lab, you know, to Director Chu, to actually make sure they have funding for young scientists to try brand new things and whatever crazy idea that they think they might want to, give them the opportunity to get some seed money and get started, and then put it on them that they have to go out and raise their own funds after that, but that they can get started and do something exciting that way. And the other is, I think cosmology's got a lot going for it. I would like to see, you know, the Cosmology Institute started up here that does, you know, not only can we continue on with the cosmic microwave background and searching for the dark energy, but we can explore the other areas of cosmology and push things forward, build up the theory and build up the other activities. And I think that's something that would be a great joint thing between the campus and the lab. But it is the kind of thing which is the kind of stability that you need, that the DOE used to perform, that you can't get from project funding, right? I mean, you can't get it from, you know, I'm gonna propose to do a flight of the U2 and to do the, you know, to measure this. That's a specific kind of thing. It's the seed money that gets started, or attack this big program. That is, those are the kind of things that are very difficult to do.